Welcome back to the Chem OG. Today I got a list of exciting topics for us. And so we're going to talk about how changing vice presidents is a negative experience. We're going to take a look at this new thing that I learned about called a term pi. And I'm going to catch you up on all the goings-ons with my best friend Kim. So I'm really looking forward to today's lesson. All right, I'll just stick to the topic then. All right. So today we're going to talk about colligative properties. And colligative properties, let's talk about what they are. They're ones that depend on the amount of something, not their types or identities. And so what we're going to do is we're going to add impurities, or we're going to add solute to our solvent, and we're going to keep track of how it is that the physical properties, or properties that we can actually monitor, how the physical properties of that solvent are going to change. And they're going to change based on the amount of the stuff we add. They're not going to change based on what they are. And so to give you concrete examples of what I mean by that, if I take a look at hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base, and I take a look at sodium chloride, which is a neutral salt, those three things in terms of what we normally view them chemically as, they're about as far apart from each other as they can be. One's neutral, one's super acidic, and one is super basics. But even though they have all these different properties, in terms of colligative properties, which are the ones that we're going to talk about today, those three molecules actually have very similar behavior. And the reason that they have similar behavior is because when we put them in a polar solution, they're going to split up into two particles. So we're sort of turning a blind eye entirely to what these molecules do normally in terms of the reactivity, and we're only going to care about one thing. How many particles can you give me in solution? And that's it. That's all we really care about for today's lesson. So again, don't take a look at all of the wonderful chemistry associated with these molecules. The thing that we're going to focus on the most is how many particles are they going to produce? And that is the big umbrella of why we're categorizing all of the different aspects of today's lesson into this thing called colligative properties. And so the first thing we're going to take a look at in terms of defining these colligative properties is we have to take a head count. And that head count is called the Hoff Factor. And so the Hoff Factor is defined as the number of particles, and I'm underlining this and italicizing this because it's so important. It's the number of particles that are dissolved per molecule of solute. So in order to have a Hoff Factor other than 0, you have to dissolve. If you don't dissolve as a particle, your Hoff factor is going to be 0. Now, the Hoff factor is designated with a lowercase italicized I, and the reason it's given that letter is because it's the ionizability factor, so that may be something that you encounter as well. But the ionizability factor can be a little bit misleading because sometimes certain particles, they dissolve, but they don't necessarily form ions. So that's the reason we're defining this here as the number of particles that dissolve. So how does that look like for specific molecules? Let's take a look. So if I take a look at something like ammonium sulfide. So ammonium sulfide, if I put it in a solvent like water, it's going to dissolve into 3 different particles. It's going to dissolve into the 2 ammonium particles. I'm going to get 2 NH4 pluses out of there. And I'm also going to get a sulfide ion, or an S2 minus ion. So those are 3 different particles. If I take a look at something like sodium phosphate is going to break apart into 4 things: a phosphate ion and 3 different sodium ions that float around. If I take a look at something like ethanol, now ethanol, if I dissolve it in water, it's not going to break up into ions. But because ethanol can hydrogen bond to water, it's going to dissolve inside the water and not break up into any individual pieces. It's just going to stay as a whole. So that's why it has a Hoff factor of 1. So the Hoff factor is very much dependent on what solvent we're talking about. So for example, ammonium sulfide, that first molecule, if I put it in a nonpolar solvent, it's not going to break apart. So it would have a Hoff factor of possibly 0 if it doesn't dissolve. But if it dissolves yet doesn't break up, it's not going to get a Hoff factor of 3. And so the Hoff factor is very much solvent dependent. A lot of times the solvent that we're looking at is water, but for the problem that you're encountering, that may not be the case, and you have to be careful about what that solvent is. Now, if I get a weak acid in water, Now, a weak acid in water does not dissociate entirely. So if I take a look at acetic acid or vinegar, for example, vinegar dissolves in water. Again, it hydrogen bonds, so it's capable of interacting with water. So even if it doesn't break up, it still dissolves, and it would have a Van Hoff factor of 1. Now, if acetic acid breaks up into 2 particles, then it would have a Van Hoff factor of 2. So does acetic acid dissolve as 1, or does it break up into 2 pieces? Well, sometimes it does that, sometimes it does that. Again, it's a weak acid, so sometimes it dissociates, sometimes it doesn't. And for that reason, it's going to have a Van Hoff factor that's higher than 1 because it sometimes breaks up, but it's not going to be as high as 2 because it's not a strong acid. So if this were a strong acid, like an HCl, which we encountered a moment ago, its Van Hoff factor would be a lot closer to 2. But you can have Van Hoff factors that are not necessarily integer values. What about something like silver chloride? Well, silver chloride is not that soluble. In fact, in water, it doesn't dissolve pretty much at all. It's got a very, very low ionization constant. And so the Van Hoff factor for silver chloride is going to be a lot closer to 0 than it is to 1. So all of these are solvent dependent, and you want to take a look at things like solubility rules for that solvent that you're looking at in order to determine how soluble that particular particle is. And if it is soluble, it's going to have a Van Hoff factor of at least 1. If it's insoluble, it's going to have a Van Hoff factor of 0. All right, so remember that Van Hoff factor. It's going to serve us well because, again, it's a barometer of how many particles are going to dissolve. The first property we're going to monitor is vapor pressure. And vapor pressure is defined as the pressure that's exerted by a vapor in thermodynamic equilibrium with its condensed phases, either solid or liquid, at a given temperature in a closed system. That's the textbook definition of vapor pressure. It's icky and it's gross and it's confusing. And so let's take that out. That's boring to take a look at. What I want to do is simplify what vapor pressure is. If you think about vapor, well, vapor is a gas. And what we're measuring is an actual property of a liquid or a solid. And so think about vapor pressure as the tendency of a liquid to become a gas instead. And that is going to clarify your thoughts a little bit because now you're thinking, all right, well, if something has a high tendency to become a gas, what does that mean? It means that the bonds among the liquid molecules isn't all that great because that's what's contributing to the liquid becoming a gas so easily. And so vapor pressure is inversely proportional to intermolecular forces. If your intermolecular forces are higher, you're going to experience a lower vapor pressure. So something like water, which experiences hydrogen bonding, is going to have a low vapor pressure as a result. And the opposite is true. If something has very weak intermolecular forces, its tendency to become a gas is going to be really high, and it's going to have a higher vapor pressure instead. So think of vapor pressure in intermolecular forces as ones with an inverse relationship with each other. And so if we think about what happens when we add solute, when we add a solute, what that does is it increases the overall number of intermolecular forces that are possible. So in general terms, this is not necessarily always true, but in general terms, what we're doing is by adding more solute into our mixture, we've increased the possibility of forming bonds. Think about a new group of students that's just entered a new school. So if a new group of students has entered a new school, there are more possibilities for friendships than there ever were, right? Person A could hang out with this group, person B can hang out with the same group or possibly a different group. But when you introduce a new group of students to a set of classmates that were already there, more friendships are possible. When we add solute to our mixture, what that does is it increases the possibility for intermolecular forces. Now remember, vapor pressure and intermolecular forces have an inverse relationship. So by increasing the possibility of more intermolecular forces, that means we're going to cause our vapor pressure to fall. And the question is, how much is our vapor pressure going to decrease by? And so the relationship between vapor pressure and the amount of solute that we add looks like this. The change in vapor pressure that's going to be experienced is going to be a decrease, like we mentioned, because when we add solute, more intermolecular forces leads to a lower tendency to become a gas. And so delta Vp is going to be the change in vapor pressure due to the addition of solute. chi is going to be our mole fraction of solute. And the way that we calculate the mole fraction of solute is we're going to take a look at the number of moles of solute, and we're going to divide that by the total number of moles in solution. So that's going to include any additional solute that happens to be in our mixture. And don't forget to include the moles of solvent as well when you're doing your calculations. So chi is the mole fraction of solute. So what happens is as the mole fraction of solute goes up, the change in vapor pressure starts to become more drastic. Now that's also dependent on P naught, which is the vapor pressure of pure solvent. Now here's a subtle thing that I also want you to be aware of, and that is the following fact. Even though the obvious relationship is, hey, as chi increases, I'm going to get a bigger drop in my vapor pressure, it's also important to note that the higher P naught is, the bigger the change in vapor pressure as well. And what that means is, if I start out with a liquid whose vapor pressure is already really high, that means even a small amount of solute will cause a big drop. Okay, so the magnitude here is dependent on both of these together, not just one of them. So if I have something that has a high vapor pressure, even a small amount of solute is going to cause this vapor pressure to decrease significantly. Whereas if I have a molecule that already experiences a good amount of bonding, well, because this number is so low, it also means that the change in vapor pressure is also going to be minimal. So if I have a solvent that already experiences really strong intermolecular forces, adding solute isn't going to have much of an effect. It already had strong bonding. Introducing more bonds isn't going to make that big of an effect. So that's our change in vapor pressure. And the change in vapor pressure is a colligative property because, as you can see, it depended on the amount of solute we added. The next thing I want to take a look at is osmotic pressure. Now, osmotic pressure is very important in terms of biological significance. And so I'm going to leave the details to sort of a more bio-based discussion. But essentially what you need to know is the more solute that there is, the higher the osmotic pressure, right? So if I have a lot of concentrated solute in one particular place, there's going to be a lot of solvent that wants to rush there. So if I take a look at the way osmosis works in a way such that whatever is a higher concentration, solvent is going to rush to that higher concentration in order to equilibrate things on either side. Which actually begs the question of why it is that people think that osmosis means the following, right, in terms of learning. So if somebody says, hey, I'm going to learn by osmosis, in other words, I'm going to learn from somebody who's super smart, and I'm going to sit there and absorb what they say. But if you think about it, that's not the way osmosis works. The way osmosis works is it goes towards higher concentration. So if osmosis is in effect, then the person who's smarter is going to get smarter still, right? Because they're going to get more knowledge going towards them. So I guess we learn by reverse osmosis. Maybe not. And so more solute means higher osmotic pressure. And the relationship between osmotic pressure and how much stuff we have looks like this. Okay. So osmotic pressure is symbolized by a capital letter pi. And it's also dependent on temperature, the Hoff Factor, R, and M. So let's talk about what each of those variables is. Pi is the osmotic pressure, as we mentioned. R is the universal gas constant. And depending on what units we're using, that's going to be a certain value. And if I take a look at molarity, molarity in this equation is measured as moles of solute per liters of solution. So molarity is a measure of concentration, as you know. And so what we're calculating are moles of solute. And it's important to note here that we're taking a look at the volume of the entire solution. So that means that we're not only taking a look at the solvent, but we're also taking a look at any changes in volume that happen as a result of adding that solute. And the T term is temperature. And you got to remember that temperature has to be measured in the Kelvin scale. Okay, so that's a brief synopsis of sort of the equation for osmotic pressure. More solute means more intermolecular interactions. Okay, and if I take a look at those intermolecular interactions, well, what that does is it makes the system that I have more strongly bonded, And it also means that it's going to take a higher temperature in order to make my liquid molecules become a gas. So more intermolecular interactions are going to lead to a higher boiling point. And that phenomenon is known as boiling point elevation. And the change in the boiling point that results from adding solute is given by this expression right here. Okay, so it's dependent on the concentration, and it's dependent on the Hoff factor, and it's dependent on a constant that has to do with that particular liquid. So Kb is a constant that's unique to that solvent. I is the Hoff factor, and M is another measure of concentration. It is molality. So it's not the same exact thing as molarity. The way that molality is measured is it's still moles of solute, right? So the numerator is still the same, because anytime we want to measure concentration, we have to measure it relative to how much stuff we got in our solution. But instead of liters down here, we have kilograms. And this is a subtle difference, but it's really important. We're not looking at kilograms of the entire solution. We're looking at kilograms of solvent instead. Okay. So previously, when we took a look at molarity, molarity was liters of solution. Here, we're only taking a look at kilograms of solvent and solvent only. So that's what happens to boiling point. Now, what happens to freezing point? If I take a look at freezing point, more solute makes it difficult to freeze the mixture. And the reason for that is, in order to go from liquid to solid, your molecules have to adopt a very, very specific orientation so that they can lock in and establish those really strong intermolecular forces that are characteristic of a solid. If you have impurities in between, it's almost like you're getting the molecules to slide over each other, and that makes it difficult to adopt the solid phase. And so that phenomenon of adding solute and preventing the frozen state from happening is known as freezing point depression instead. Okay, and that's because the freezing point is now going to be lower than what it was before. So if your molecules are sliding over each other because of those impurities, it's now going to take a lower temperature than the previous temperature in order to make your molecules freeze. And so coincidentally, this is the reason that in cold weather locations across the world, one of the things that we do is we salt the sidewalks. So by adding salt to the sidewalks, when the cold front comes in and when snow seeps in, if that snow starts to dissolve all that salt, instead of being frozen at 0 degrees Celsius, now that water freezes at -3 or -4. Right? So when your temperature nears the freezing point, if we're only at -1, -2, without salt in there, your water is frozen. But with salt in there, your water is not frozen. It's a little bit liquidy, and it's a little bit easier to move water than it is to move ice. And so Kf, again, is going to be a constant that's unique to the solvent that we're looking at. I is still the Hoff factor, and M is the molality, and that's measured in concentration units of moles over kilograms, as we mentioned. Okay, so we brought that whole molality thing up more than once now. Why is it that for certain situations we use molarity, like an osmotic pressure, and why is it that in certain other situations, like freezing point depression and boiling point elevation, we use moles over kilograms instead? Well, let's take a look at those two measures of concentration. And so molarity uses liters of solution, and that's fine, right? Because if we take a look at osmotic pressure, with osmotic pressure, we're trying to push the entire solution, so it makes sense to take a look at the liters of the entire solution. But what that also introduces is the fact that when you change the temperature, the volume of your solution can go through slight changes. And that's important to note because by changing the temperature, we can change the molarity of our solution, even though there's been no change in the number of moles of solute present. So I'll say that again. Because temperature can slightly affect the volume of your solution, it means that your concentration and molarity can change, even though you didn't add anything and you didn't take anything out. If you want your concentration, on the other hand, to be only a reflection of the particles that are in solution, and you don't want it to be temperature dependent, then you want to use molality instead. Okay, so molality is not dependent on temperature. The only thing that is going to affect the molality is whether you add in solute or you take it out. Your kilograms of solvent is not going to change, as temperature changes. So to summarize, here's what we got. A change in vice presidents leads to a negative experience. Oh yeah, that was relevant. I wasn't talking nonsense at the beginning. If you take a look at the equation for vapor pressure depression, that's how it looks like. A change in vice presidents leads to a negative XP, negative experience. Remember that pi term that I was talking about? Pi equals term. That's the osmotic pressure equation. And Kim, my best friend, well, check it out. She helped us through our highs and our boiling point elevations, and she helped us through our lows in terms of our freezing point depressions. So delta T equals Kim in both of those situations. And whether it's the boiling constant or the freezing constant, those are reference values that you can look up or given to you on the exam as necessary. And remember that adding solute, what it does is extends the liquid phase. And so what I mean by that is it caused our boiling point to go higher. Why? Because the liquid phase is extending itself a little bit and it's not allowing the gas to form when you add solute. The other thing that happens when you add solute is that your freezing point goes down. And as your freezing point goes down, that also extends the liquid phase. So we're extending the liquid phase in either direction. We're making it harder to go from liquid to gas, and we're also making it harder to go from liquid to solid. Thank you for watching today's lesson. Don't forget to like and subscribe.